Hi, I'm Sebastian Wloch, CEO of Episodio, and today we're going to talk about aerodynamics. When we started working on Microsoft Flight Simulator, we first studied all the code that has been written on Flight Simulator X. There's been many years of work on all the code base, and the code base of the simulation of the aerodynamics was pretty huge. I will cover 5 areas of improvements that we made to the Flight Simulator aerodynamics and physics. First, we made improvements to the core simulation engine. Second, we made improvements to the actual simulations of the different systems of the aircraft. Then the biggest area we reworked was the aerodynamics. We reworked the aerodynamics simulation from scratch in the simulator. I'm going to go over the details of how the aerodynamics simulation now works. One big area that we reworked was the weather system. The biggest interaction of the aircraft is with the air. It's the air that makes the aircraft fly. And so we reworked how the air was simulated in the world, creating a full simulation of the airflow over the planet. And I'm going to explain how the airflow interacts with the world, the environment, and also with the weather. The first big improvement we made to the core of the simulation is a better collision model with the environment. So the system now supports sloped surfaces, which means that aircraft can land on sloped runways, but also on any slope in the world. Aircraft can now land on a sloped field. For example, if you want to simulate an engine failure, you can make a cross-country landing on any surface, including sloped surfaces like fields on mountain slopes. It's gonna work anywhere. To make sloped surfaces work, we had to rewrite the friction model of the aircraft. So tires are now correctly simulated with dynamic friction, static friction. All the friction parameters have been improved, and so like the rubber now really behaves on all different surfaces like tarmac, cement, grass, earth, exactly like it should. And also on slopes, if the tires start to skid, they're gonna skid exactly like they should with realistically simulated dynamic and static friction. So we also improved the way the bumps on the ground are handled. They are now realistically simulated, and the way the brakes are simulated. So this allows for planes to come to a full stop even on slopes, and that's when they transition from dynamic friction to static friction. And planes can really come to a complete halt exactly as they should on slopes. So when you do a landing on a sloped runway, you can now roll and you can stop on the slope, turn around and take off again. We also rewrote the integration system of the simulation. So the integrator is what makes the simulation go forward. It calculates all the states of the system. So one thing we changed is now that the simulation is running at a much higher frame rate, but the frame rate is adaptive, so it adapts to the frame rate of your actual TV or monitor. This means that the simulation is much more smooth. Whatever the frame rate of your display, even if you have slower frame rates, frames are exactly going to match the display. And also the simulation is always going to run at a higher frame rate. So even if your frame rate goes down, the simulation stays at a high frame rate and you don't lose anything of the realism. Planes always behave as they should, whatever the frame rate. Another big change we made to the integrator is the way the integration now works is much more realistic, and it has removed one artifact that was present in previous versions of Flight Simulator, which is that planes felt like if they were on rails. It's because the old integrator was resisting change, and it was forcing planes to always move more or less in a straight line. So the integration is now super realistic. It's exactly moving the aircraft as they should in the world. Spins are much more realistic now, and planes don't feel on rails anymore. So we changed that and removed the effect of planes being on rails. We also reworked the inertia matrices. They are now more realistic, which means that the mass distribution of aircraft feels more real, and planes, when they rotate, when they yaw, when they pitch, when they roll, they feel much more realistic now as they travel through air. So we also made improvements to systems in the simulation other than aerodynamics. We improved the load factor simulation, which also improved the way the ball, the turn coordinator, is simulated. It's now much more realistic, which means that when you fly asymmetric, which means that if your aircraft skids a little, the ball is moving to the side exactly as it should. And you can now control with the rudder your flight and make it symmetric using the ball much more easily, because it reacts much more realistically than before. And so we have now specific fuel consumption, which is realistic per altitude level and which is matching the actual POH of the aircraft. We improved the way flaps can be set in the files, which allows to have more control. We finally reworked the way gears and external parts like external tanks are simulated. Instead of just hard coding the moments they apply on the aircraft, they are actually physical elements in the airflow which are attached to the airframe outside of the aircraft, and they now are realistically simulated aerodynamically just like the aircraft and apply their own forces and moment exactly where they should, how they should. We also improved the icing system. So icing is now simulated realistically depending on the actual humidity of the air around the aircraft, and because the weather system is now accurate and simulated volumetrically, if you fly through clouds, you're going to get a different icing than if you fly through dry air. And so this is now simulated in 3D volumetrically. Also, what we did is the legacy simulation code from Flight Simulator X is still available. So you can switch to the legacy simulation if you don't like the new simulation. We don't want to force anyone to move to the new simulation. So all aircrafts have been reviewed with professional pilots who have many hours flying these aircrafts, or test pilots from the manufacturers. So we've gone over the aircrafts which were already matching POH when we presented them, but to make sure they actually are controlled exactly like they should. There's many parameters that we set that are not actually present in POH, such as how fast the aircraft is going to roll when you move the yoke to the left, for example, depending on your airspeed. This is data that is not always available, but that professional pilots feel. They know how agile the plane is at what speed. And so these are parameters that we set with them, and we reviewed the whole aircraft to make, for example, stalls as they should be, or if an aircraft can spin or not, or the way basically they behave so that they don't just match performance parameters from the POH, but actually feel as the real aircraft when you fly them in real life. So the big change we made to the system is the aerodynamic simulation has been reworked. So how we simulate now is much more advanced. So we subdivide the aircraft into thousands of surfaces which are mapped over the airframe. So for example, over the wings, over the fuselage, over the wheels, over the tail. There's thousands of little surfaces which are placed exactly where they should over the geometry of the aircraft. Each surface goes look at the weather, so it has its own wind direction. It's going to have its own air pressure, its own humidity. This means that the right wing, for example, can fly through a cloud where the left wing doesn't, and you can have different wind, turbulence, and humidity on the right wing. Each of these surfaces has a realistic airflow simulation. Each surface is going to have its own wind direction, its own air pressure, and it's going to do a full three-dimensional calculation to compute what is the force and moment that should result from the airflow flying over the surface. This simulation includes the airflow, speed and detachment and orientation. It will realistically simulate stall. The stall is when the airflow is actually bent too far by the surface and the airflow cannot stay attached to the air surface anymore. So this is now simulated surface by surface, which means that we can have a left wing stalling, especially because of the weather and the full realistic simulation of each surface in the world. But each surface will also deflect the airflow. The airflow is going to be impacted, and surfaces which are behind are going to get a different airflow because the airflow was impacted by the surfaces in front. So this, for example, is going to allow more aerobatics. So for example, the airflow is coming from the propeller and is hitting the tail, and that's how you can, for example, enter into a flat spin or some of the figures. So for example, when you can do an inverted spin, that's because the propeller hits the tail, and this is now realistically simulated. The big improvement we made to the simulation is the simulation of the air mass. We now simulate the air mass globally over the entire planet and realistically. Every area of the world has its own simulation of air, and we know where the air is flowing everywhere on the planet, and this then feeds into the aerodynamic system of the surfaces of the aircraft. So this means that, for example, we will have volumetric clouds, which you can see in the world, which are going to match the airflow. For example, on TCUs, on towering cumulus clouds, usually it's a kind of cloud which exists because there's a lot of updraft of air. But when they get really big, there's an updraft on the side, and in the middle it actually goes down. That's basically why they're so dangerous, and you should never in a small aircraft get close to a TCU. In a big aircraft, you're going to get a lot of turbulence. And so this is now simulated. The airflow in the world is going to match the clouds, and it's going to fly. The air is going to move up and down inside of the clouds. So you will see a video which is going to show this airflow. So in order to visualize the airflow, we released thousands of particles in the world and displayed the trajectory of the particles. They just do exactly the same calculations than the aircraft in the world. So each particle samples the world atmosphere, exactly like each surface on the aircraft. So you can see on clouds that the air is moving up and down. You can see the turbulences, which is when the airflow of the particles changes color and the particles move more randomly. So these are like wind shear or turbulences. Some of the air may go up because it's in the middle of the cloud, some may go down, and at the edges you get shear. So this is all now naturally simulated, and we have all the updrafts and downdrafts in the world which match actually the weather. So this air mass simulation also works with the world shape, like the shape of the world, which can depend on buildings, hills, forests, mountains, valleys. So all these different shapes worldwide are going to influence the airflow in the world. So for example, the air flows over a stadium or a hill. It's going to create updraft, so the wind is going to flow up. And on the other side, usually it goes back down, but in a turbulent way, right? It has to go back down, but it's gonna be creating a lot of rolling turbulences. So you can imagine when you fly over this air with the aircraft, if the aircraft is flying slow, if it's a small aircraft, it's gonna get all these rolling moments, it's gonna get the up and down draft, and you're gonna feel all these bumps. So on the video you're going to see there's, for example, wind flowing over mountains, and it naturally creates turbulences. On the other side, in the valleys where the currents come together, they collide and it creates these turbulences. You can see in the middle of the valley, you can see the up and down draft, and you can see how the slope of the wind is actually very, very steep, right? It goes along the slope. So this is it for the improvements on the aerodynamics, on the physics. So we improved the core simulation, we improved many of the simulated systems, we reworked the aerodynamic simulation with the surface-based system, and we reworked the simulation of the airflow in the world. All these changes come together to create a much more realistic simulation of the aircraft. Aircrafts are now simulated realistically to the performance data that is available. They fly exactly to the real-world performance, but they also feel exactly like real aircraft. They turn, they behave when you move this yoke exactly like a real aircraft, and they fly through the world. They fly through the air exactly like a real aircraft flies through the air in the real world, being impacted by clouds, by mountains, by buildings, by the shape of the world, right? I hope you enjoyed the details I gave about the simulation, about what we changed. Thank you for your time. Please subscribe to the Alpha, and talk to you soon. Ah, tu pourras le couper ça.